So today, just to set the stage, we'll be talking about conservation of momentum. And of course, conservation of momentum is how we do useful work with machines. And so to generate electricity, typically you want rotational motion around a spindle, to have a coil running through magnets to generate. And so turning linear motion, which is the motion of this jet of air, against this Pelton wheel. Pelton wheel is just a whole bunch of cups arranged around a spindle that scoots around when you blow fluid into it. And so that basically transfers the kinetic energy, the momentum, if you like, of the jet into rotational motion that can do useful work. And so that's kind of the idea of why we might be interested in this. Same idea for a wind turbine, same idea for a pump, doing the opposite things, right? Pumping water to gain potential head as a result of moving it in elevation. And to move it in elevation, you need to be able to pump it out of the well or somewhere else. We'll talk about first linear momentum, which is what this is. The previous one was kind of rotational momentum, and we'll deal with that last on Friday. But this is the jet lev, the so-called jet lev. There's a narration that goes to this, but apparently it won't play. And I don't know if this is a $15,000 thing or a $50,000 thing. It's one of those two. You can go and check it out if you want. But quite a cool deal. I guess I remember seeing a news article saying that someone rode one of these across the strait to Catalina Island from LA. If you fly out of LA, you usually take over the ocean, head out of the ocean, head out over Catalina Island, then head back east to DC or wherever. But at Catalina Island, probably, maybe 5 miles, 10 miles offshore. So someone ran one of these. So what it is an umbilical, the yellow tube behind. The umbilical couples up with a float that comes behind you, which has all the business end of the craft in it. So it's a pod like one of those Thule ski rack boxes you see on the Thule ski rack boxes you see on top of cars, and that has a pump in it. The pump supplies water at pressure, and then the pressured water is just like the jet we saw with the guy with the little jet engines on his wrist. But this is, instead of transforming chemical energy into moving air, this is probably an internal combustion engine pump, pumping up water pressure and then using the water as the jet. Kind of cool. I think it is either 15 grand would be a lot for me for this. 50 grand would be a huge amount for this. If you've ever worked in a lab or plan to work in a lab, one of the things they'll always impress on you is the idea of safety with the sleeping giant, quote unquote. And the sleeping giant is the gas cylinder that gets decapitated by falling over. The cap comes off, and then air under pressure. The highest pressures of these are probably about 70 MPa. I remember we ordered one once. And so this is Mythbusters. You must have seen this in your past, or it's kind of contemporary of yours probably. I don't know if they still have it or not. But they're doing a little test to see if the myth whether this can travel through walls is true or not. And so that's exactly what they're going to set up here. We've used this before. I've never had copyright claims on this. They're using a guillotine to decapitate it, and they're looking at what happens to it. So it's on some kind of runway, gets decapitated, basically a rocket, right? With all the stored potential energy in the gas under pressure, which in a rocket is produced by the burning of a fuel, an expansion, but the same idea, some way to make a jet that has a pressure in it. And what happened? And so what happened is that it went through a wall. I don't know if it went through a second wall, but so the reason that people belt these, attach them to table legs so they're vertically and can't move and can't fall over is exactly this reason. So it's not very difficult to imagine what I guess if you're on the 5th floor of Dyke or the 2nd floor of Hostler, and one of those came through an outdoor wall and landed in the parking lot, I guess that would be a kind of an interesting sight to see. Yeah, okay, so you said. So there. And what else have we got? And so you have to listen to my narration. That's not so interesting, but maybe we'll play it anyway. Why not? If you've got a propane torch, yeah, actually it goes a long way. So ideas as well, I guess, for your projects, which are due Wednesday. I saw that Jai sent out an email on the weekend, and I got a couple of emails from people seeking partners in their groups as well. So I know people are kind of motivated to do that. So that's great. And so another example, perhaps not so obvious, but certainly the idea of a weir. I guess it occurred in our time when we were taking the test. The examples of using undershot weirs, overshot weirs, the idea that you can measure flow rates as a function of putting an obstruction in a surface water flow. You measure the difference in heads upstream and downstream, on upstream and downstream of the gate, and you use that to intrinsically define exactly what the flow rate is. Much easier to figure out flow rates using either pressure changes by staunching flow like a pitot tube, or by using head changes, elevation changes, which are really pressure changes between upstream and downstream. It's much easier to do that than measure volumes. Volumes would be filling a bucket with the water that comes down the river, which is obviously not very convenient, although it can be done, right? So I don't know if you still see them these days. There used to be gas pumps. You'd see a little open, visible node in the side of the tube that comes to fill your car, and it would have a four-faced wheel, like a water wheel in it, that would just rotate. And it would take water into one quarter compartment, and from the upstream side, it would turn it around and send it downstream. And so each time it did that, it would meter out a certain volume of fluid. But generally, if you want to get flow velocities for structures like this, or flow volumes through a pipe, it's much easier to measure pressures, and then we can do that using the principles of Bernoulli in this particular case. So that's kind of what we're up to for today. So that kind of sets the stage. So where we are is that we've just moved from one topic to another. I can get rid of this. So this is our topic for the day. So as normal, we'll go through a recap and say something about what we've done so far. So you remember that weeks 4 and 5 were Bernoulli. So we defined Bernoulli. And Bernoulli comprised two separate things. Don't worry about those equations. And let me come back to them. So 4 and 5 was Bernoulli. 6 was conservation of mass. Remember on Friday we filled up a bucket 85 different times. We used 3 methods. We used the pipe static coordinate system. We used a moving but not deforming coordinate system, and we moved a moving deforming system. The only ones that were really useful to us in that were the moving non-deforming one, because the top of that coordinate system moved up to the top of the bucket, and so the time at which it hit the top of the bucket was when the bucket was full, and we could use that directly. And the other one was the deforming one, where we anchored it at the bottom of the bucket, and it grew with time until the top surface hit the top of the bucket, and that also defined exactly how long it would take for our bucket to fill. So those are the 2 useful ones out of the 3. But if you recall, what we did last time was that we took this relationship, we defined that for conservation of mass, this B value was equal to mass, and the lowercase b value was equal to mass over mass, b over mass. Go back. So these terms ended up being, this ended up being 1, this ended up being 1, this ended up being 0, And we ended up with a very relatively straightforward relationship, which defined our behavior, which is written on the left-hand side of these, which was that if we want to get flow rates, then we define this outward normal idea, and we also define two flow velocities, V2 downstream, just out of convention, and V1 upstream. And if we did that, we could write the equation in terms of this form. And all it said is that within the controlled volume, the density times the rate of change of volume plus the volume multiplied by the rate of change of density plus, I guess I'll write it out again, sum of mass flow rates equals something that doesn't move anymore. Oh, this is going to be a fun trick. I don't know what that is. Have I lost Bluetooth or something? There's my whole computer hung. It moves to the cursor, but not for the pad. Why is that? 42% full. I guess you can see that as well as I can. Oh, this could be a challenge because then I'd have to use notes where I wouldn't, right? Much easier for me to do that, but much worse for you, I think. Just trying to pair. It's not it, right? Bear with me. Well, I could try writing with a blunt object. Well, okay, right. Didn't mean to do that. All right, okay, well, plan B. Is it working now? No, it's not. So, right, well, plan B is to do this. So the important things to realize is going to be, I guess I could run last year's class. That seems kind of retrograde to me. But the idea, well, this is the expression here. The idea is that we can write the expression in terms of an accumulation term and a flow in, flow out term. And the idea is that we've dealt with this before, because we talked about conservation of mass when we talked about Bernoulli, and we wrote it merely as velocity times area in at the upstream is equal to velocity times area at the downstream. We can multiply both sides by density to get it in terms of mass rather than instead of volume rate, mass rate instead of volume rate. And so this expression here is just our Bernoulli term that we've written in a different way. The sign convention, which is important to us, is that if it's out of the volume, it's positive. If it's into the volume, it's negative. It's defined by a dot product, but we're not going to worry about that because will either be directly across the face or parallel to it. You'll see that the faces which are parallel to the flow between upstream and downstream, there's no fluid going across those, so there's nothing going out. So the mass rates are zero across that. You'll note that the mass rates are a scalar quantity, in or out, not directional, once we've multiplied them by this dot product. And so our term that we have here is really just what we use for Bernoulli, but with this accumulation term. And so the idea with Bernoulli, within a stream tube, the stream tubes represent streamlines which a particle will flow. So by definition, the normal velocity to that streamline is zero. So it's the same as the top and bottom of our control volume. And so this is just saying that Bernoulli is steady state. If we don't want it to be steady state, then we can change the amount of mass that goes in. For instance, if the outlet velocity is zero, but the inlet velocity is finite, then you have to do one of two things. you either have to make the volume bigger to accommodate it, so in other words, filling up a bucket where the control surface moves with the top, or you have to do it like a tire where you increase the density in a static control volume, and this term increases. This will always be, this should be a negative in this particular case. I guess we didn't care since this is a 0, but this would be a negative because it's a mass rate in if it's coming in from the left-hand side. And so that's where we came from. Okay. So that's kind of where we went. I don't know what to do now. Oh, God. Well, we all get used to technology. And I'm guessing it's not going to change. This obviously works. But my pen, let me try again, since it's... Oh, we're in luck. Okay. So anyway, so I guess perhaps we'll get less done. So in other words, this part here was equal to V1 A1 rho plus V2 A2 rho and equals 0. I guess I didn't get to drawing this. So in other words, when we've talked about a streamline, which perhaps is an easier concept to define, if we have V1 and V2, I'm probably spending more time on this than I want. This is Z2 and P2, etc., you know, from Bernoulli. But when we solve for these, we solve two things. We solve Bernoulli equation, which is this. And you'll probably be well used to using this by now, which is for inviscid flow. In other words, it has no viscosity attached to it. And so this allows us to be able to define the behavior in terms of velocities if we have enough components to solve it. If we, for instance, have two unknowns in this instead of just one unknown, then we need another constraint. And so this term here is equal, let's write it in terms of what we're talking about. This is conservation of momentum, and this is conservation of mass. So this is what we spent our time on last week. This is what we'll spend our time on this week. And so the idea here is, and I was going to write it out, is merely, instead of writing rho 1 A1 V1 equals rho 2 A2 V2, I think you can see, we could change that around, and we could write it with respect to 0. That still satisfies that equation, and we could add these two terms here on the front. So these two terms would go here. And so that means that for our geometry, you know, we've talked about it in terms of this geometry where there's no flow across this boundary here. But of course, for a streamline, the individual flow lines would be in this direction. And so by definition, this is our control volume within a stream tube. And so what we're putting in is fluid according to this relationship here. So these are the changes in volume that can occur. So we're making it more general, if you like. So when we solve problems using streamlines, we used Bernoulli. We noted that Bernoulli gave us a force, and this was, other way around, right? These two terms here were a force minus mass times dv dt. This is acceleration, etc., equals 0, and both sides equal 0 in this particular case, and we could write it in those terms. So Bernoulli allowed us to be able to solve these problems in streamline geometries. What Reynolds' transport theorem allows us to do is to solve it in any arbitrary geometry that we want to. And of course, we've kind of solved it in that way, right? Because if you remember, don't think we're going to get as far in this class today as I thought, but that's fine. You'll remember this little ditty that we had before, that was the velocity 1 coming out of a jet engine and the pressure 2 at which it hits the truck. And we could simply write Bernoulli as V1 squared over 2g is equal to P2 over gamma. And we rearrange that to get P2, sorry, I said P2, but I wrote is equal to V1 squared over 2g times unit weight. I guess this is rho g, so the g's cancel out. And so then this defines the force that gets applied that has to be reacted against on this. And so that's what we will attempt to do. We did it for Bernoulli. So now our approach to this particular topic would be to do something like this. We would have a control volume. I guess the control volume, let's just have a control volume that looks like this. The control volume allows us to get this velocity coming in, V1, a velocity going out, Vy, or Vz, I guess, what we've seen. And what we're doing is we're converting this velocity into a pressure which is resisted by this force. And so what we're trying to do is we can solve the same problem we solved with Bernoulli, but we'd solve it on a control volume that we choose, and the control volume will look something like this. And so to do that, we just go back to this idea here. We said that the quantity that we want to conserve is defined as B. It was mass. Now it's going to be mass times velocity. That means that lowercase b is going to be equal to mass times velocity over mass, which equals velocity, not volume. So this is what we did in week 6. This is what we're going to do this week. 7. And the idea is that this, instead of being 1, this would now be, if I get rid of them, this will now be velocity. This will be velocity. And this will still be, this will end up being change in velocity. That's right. And so if we think about what this is, a rate of change of mass versus of velocity. So if we write out a rate of change of mass times velocity dt, well, you can think of that as being Newton's law, F equals m dv dt, right? If we ignore this, the mass is included here. So this term here is going to be a force. So this term here is going to be sum of forces. We're only going to look at steady state behavior, so we're not going to look at rates of change of momentum. So we'll always set that equal to 0. And you see that now we have 2 velocities in there. So we had what we had before, which was a mass rate, but now we've added a velocity to it. And so what we could do is we could write out this expression as sum of forces is equal to, I'm going to include this term. This is rate of change of density, velocity. No, I'm not going to include it because we won't use it. I'm going to include this term. So what do we have here? You know that the density and the normal to the boundary velocity times the area, all these blue things we defined as a mass rate, right? Which was equal to density, normal to the boundary velocity, and area, right? Area, normal to the boundary velocity, area, normal and density. So this term here. And so we're merely going to write this out as equal to sum of mass flow rate. Did I do a dot on it? I should have done, yeah, I did a dot. Multiplied by velocity. So that's it. So that Reynolds transport theorem comes out to being this. And if I move this over, just because I can, because I'm going to try and explain it. Oh, God. I'm good. I know you don't believe it. Rate of MV accumulation plus this. So that's what the full term is. This second term that we're not going to speak of is the rate of accumulation of momentum, right? It's kind of a strange concept, the idea that you could accumulate momentum, but it's much easier to think of in terms of mass, right? You put mass into a bucket, the volume, the surface goes up, so you're accumulating mass within a bucket, and so mass rate in minus mass rate out equals mass accumulation. So it's the same for a control volume that has momentum going into it. Now what is going into it is this velocity, but it also has a mass rate attached to it, and it also has a mass rate attached to it going out. And so momentum in, momentum out. If they don't balance exactly, then they will equal an accumulation. So this term here that we won't speak of anymore is how much it accumulates. So we'll assume that this is equal to 0, just because it's easy. And so what it says is that the balance that we have to do is, I'll just write this out in a less complicated way, sum of velocities times mass rate of accumulation. And we can use the same ideas as before. The only sticking point is that, you remember when we used Bernoulli, we look at a streamline velocity. And of course the streamlines go in and then they go up and around the structure. I guess they'd be a bit closer to it. So the streamlines would do this. And so the idea is that this velocity is normal to this velocity. And so momentum, instead of being a scalar quantity, has direction as well. And so we have to resolve forces in the 3 directions. So this would be a vector, and this would be a vector. And so I guess if we wrote it out, it would be sum of forces in the x direction, forces in the y direction, forces in the z direction. These would be individual equations, equals mass flow rates times, I guess, let me write them all together. Mass flow rates times velocities in x, mass flow rates times velocities in y, and mass flow rates times velocities in z. And so it's a vectoral quantity that we have to worry about. And so here, there's going to be a net force because there's momentum coming in, then it shoots up vertically, so that doesn't count in terms of our accounting for momentum. So basically we're balancing this momentum here with the force that it generates. And so it would basically be this top equation. Just one. We only need to worry about one in this particular case. So that's kind of it. So we need to be, so I think you need to see a parallel between these. So before we talked about Bernoulli in weeks number 4 and number 5. Sorry, the other way around, isn't it? This was number 5 and this was number 4. And so Bernoulli will allow us to be able to do this calculation. If we don't have enough variables, then we do conservation of mass on it, and we can do that. Here we do it in reverse order. We talked last week about conservation of mass in terms of this control volume. We talked about the expression that defines it. And perhaps I'll just write down here so it's clear for everybody. If we look at momentum, and if we talk about mass, the two expressions, density, rate of change of volume, plus volume, rate of change of density, plus sum of mass rates equals 0. And in terms of this diagram, we defined velocities v1 and v2. And so in terms of conservation of mass, then this was positive out, and this was negative in. When we talk about momentum, we're defining, and we'll do it one equation at a time, so let's just write x is equal to the sum of velocities in x multiplied by the rate of changes of mass. So this summation of mass is the same convention as this, but importantly, when we talk about, why does it do that? When we talk about conserving momentum, then this goes with the coordinate system. And so the coordinate system for this would be x and z. The coordinate system for the boundary would be a normal, which is controlling this one for the mass rate. And so this is positive in the direction of the global coordinates. So this one will also be positive, but this one will also be positive. So v1 is going in the direction of x, and so that is the global coordinate system that we use for that. And so that's really all you need to know. So I'd say that this is probably an important little panel here in terms of defining what's going on. And so I'm just trying to make the point that it's not very different from what we've looked at already, because it's the same as conservation of mass using streamlines and conservation of momentum using Bernoulli. It turns out to be exactly the same relationship. It's just that it can be a stream tube like this, where these individual velocities are parallel to the flow line, and so there is no normal to the boundary velocity. This is equal to 0. And likewise, there's no velocity out here. So this, you could think of this as a stream tube, just like a squat stream tube. So that's it. So what are we going to do? So we've got rid of a bit of math here, blah, blah, blah. So it might be interesting to be able to do this example. And so here's an example to do exactly the geometry that we looked at before. And so the question really is, if you have a weir which is set up across a stream, and you put that weir down, a gate I suppose, then can we calculate the pressures or the reaction that is applied on this gate to be able to stop it moving, this reaction? Yes, we can do that from statics. What happens if we lift this up? Is the force that's applied on this gate now, the reaction, now larger or smaller than it was before? So that's basically the question. It's all written out here from the book, but let's just, for the heck of it, go through it in real time. So I'm feeling cocky this morning that I can actually do this for you. So this is the deal. So we have some water. We have a gate. I'm going to make that's why don't I do it bigger so that it's this gate comes down to some amount. I think this is the plinth that it sits on. I suppose we would have water coming out of here at some rate, maybe, but let's not do that. Let's put the gate all the way down first, and let's do the calculation. So this is, they call it uppercase H. It's of width B, I think, into the page. That's not bad, is it? What else do we need to know? We could calculate exactly what the force is acting on this gate, if that's the case, right? So this is where there's no static fluid behind, and we're talking about applying a reaction in the x direction. I guess we can draw x and y directions, x and z directions maybe. So what's the magnitude of Rx? Rx is equal to the resultant. The resultant is equal to HC gamma A. HC for this is going to be H over 2, right? Gamma is going to be gamma W, and area is going to be the product of H times B, the width. So H squared B gamma over 2. So we're familiar with that magnitude. So that's what it looks like in that format. So now what happens if we take it and we modify it so that we get rid of this and we get rid of this, and I redraw. I realize that you might be scrambling to redraw this. So now we get water flowing under this gate at some rate. And so now we want to be able to change this. So I'm going to do a slightly different control volume. I'll do it in green so you can see what's going on. And so let's now take a control volume where we've raised this gate, and this control volume isolates this. And now we're going to look to balance Rx, the reaction on this front gate, still a gate, with everything else which is happening. So what's happening? Well, clearly we have, and if we use Bernoulli for a free jet, we would get V2. Clearly from Bernoulli we'd have V1, and I guess this would look like, I can use this black line just to be able to draw those. These would be uniform velocities. So V2 might look like this on the bottom. And behind the gate, I don't know if I can move it. I think I can't because I'm right at the edge. But behind the gate we would have this pressure distribution. I'm running out of space, but you know it's triangular. And this has to be the same one that we calculated before, F sub r. It's going to be this, right? It's going to be nothing different from that. It's acting on the back. It was the full height of the closed gate. Now the gate is open. Now the gate is also open. And if we look at the forces that are applied, I've drawn this here. Let's leave it there. But there's also a pressure distribution acting in the water. And this pressure distribution is a linear one. I should have drawn it here because the V1 and switched them around. But this would be F2. Those would be pressure distributions. And I suppose those amounts would be acting in this direction here. And so that's kind of the components that we have acting. We have forces upstream and 2 downstream. And we have velocities upstream and velocities downstream. We can use Bernoulli if you want. We can note that V1 times H times density is equal to V2 times lowercase h times density. And so from that we can calculate that, I guess we could multiply both sides by B as well, the width into the page, to get a true volume. So from that we'd end up that V1 is equal to H over H times V2. So V1 has to be, you surmise that V1 has to be smaller than V2 just by a ratio of those two heights. Makes perfect sense, right, I think? So that's our mass conservation. It's steady state. So now if we look at conservation of momentum, we know that the sum of the forces is equal to the sum of the velocities we only need to resolve in the x direction, multiplied by the mass flow rates across those boundaries. So, I'm going to go back to using a less blunt instrument than I had before, since I've got the diagram drawn. So the sum of forces will be Fr, positive. Will resolve in the positive directions of x, minus R sub x, minus F2 is equal to the flows through the system. So we have two flows. So this is velocity 1 times mass flow rate. Let's write mass flow rate out as velocity 1 times the area. So this isn't over A, but this is, I can't draw brackets properly. Let me try and draw a bracket, see how crappy it is. So in other words, this is a squiggly bracket. Height times this, so this is velocity, times density. So this is, remember that the mass flow rate is rho AV in terms of this. So this is rho AV. And the other term is we add this one here, which is uniform across it. We can choose it to be anything. It's going to be V2 times lowercase h times b times rho. So this again here is area. Perhaps I should just write it above it. Area. Okay? And so now what we have to do is we have to figure out our sign convention. Right? If we go back to our sign convention, we said that mass flow rates were positive out and negative in, but the velocities that go in front of it in our particular term, so this is a dot, uppercase N dot, are positive in the coordinate directions. So what would that be here? If this is what we're taking as the mass flow rate, M1, then this would be going into the system, so this velocity would be a negative. If this is mass flow rate 2, then this velocity is out of the system, so this would be a positive. The velocities otherwise, multiplying it by for the momentum, m times v, so this is this one here, are positive in the directions of the coordinate direction. So this is going to be positive in this direction, so they'll both be positive, right? And so that's it. And I think in the example in the book, they also have a shear stress on the bottom, a shear force on the bottom that you could add to the viscosity of the system, F shear, but we don't know what that is. So I guess that would be added on this part here, but won't worry about that. And so we just need to be able to define things in terms of this. So we can move things around. So Rx is equal to, let me get some space. This is what we want, this term here. Minus Rx is going to be equal to minus Fr plus F2 plus, I guess minus, right, because of this, minus V1 squared HB rho. These are both pluses, plus V2 squared lowercase h b rho. And so I suppose we're interested more in the positive value of Rx. So we can make these, I'm just going to change them to be the opposite. This will be a negative, because I can never track these things very well. So it's been kind of a leisurely, hope it's not too slow for you. But we can make the case that this is the resulting expression. And it's kind of an interesting expression. Obviously, all of these, a couple of things to note. One is that because the velocity times area, upstream and downstream, are balanced, they cancel out. And so if that was just a mass balance, those would be the same as the same size terms in each part of the equation. But because in the momentum equation it's v squared, so there's a v in here and there's a v here, then this higher velocity, which it has to be here, has much more impact. And so if you look at this term here is going to be large. This term here we can probably take as being 0. It will be close to 0, right? The higher this gets, the smaller velocity 1 will be to satisfy this outflow. And because it's a squared term, then we can probably throw away this term. So maybe we don't have to worry so much about this term. And in the example, they do exactly that. The other thing is that this reaction now is equal to what it was before. So we said before that the reaction and the force acting on the back of the gate when the gate was fully down were exactly equal. So these two terms previously were exactly equal to each other. But now, when the gate's up, this is equal to each other. It's minus a small force which is acting back on here, and it's minus a big velocity that's coming out of the bottom of the gate. And so the net, since these are both negative, and I've conveniently thrown this thing away because of the argument I used, is that you can come to the conclusion that the reaction working on the gate when the gate is up is less than it was when it's static. So it's much less force applied on the gate when it's open at the bottom because you're letting water out. Perhaps that's self-explanatory or intuitive. I don't think it is, but that's the reality. And we've shown it by this. And F2, of course, if you wanted to calculate F2, well, you know how to do that. F2 would just be equal to the height of the centroid multiplied by the area times the density, which would be equal to the height of the centroid is h over 2, lowercase h over 2. The area is h times b, and the density is density. Right? Has to be atmospheric on this surface, so it has to be a linear distribution from the surface. And so that's why this distribution is here. It's the same form as it is on the back gate, but it's just a smaller height. And that's it. So well, that's actually good. So maybe I recovered from a disaster of the pad not working. You can see that exactly here. And if you want to go through it, you'll see that epitomized, if you like, in this final expression. Is that a stretch or a hand I saw in the distance? Stretch. Stretch. Fine. So this is a reaction. It's equal to, this is F sub r, what we've called F sub r, which is this, what was the reaction before. Well, I won't go back. Yeah, we just talked about it. It's equal to this amount, but it's minus the pressure acting at the lower small portion of the gate of height h. It's minus a frictional viscous force on the bottom of the gate, if we have that. If you look at this diagram, there's a frictional force acting on it. It's minus the velocity coming out of the gate squared, v2, and this small amount, which will be smaller, even though it's a large amount here, because the upstream velocity is squared. This very small velocity squared isn't as big as a larger length multiplied by, a smaller length multiplied by a much bigger squared velocity is a larger feature than a bigger length multiplied by a much smaller squared velocity. So, makes sense. And so I merely conclude from that the force acting on the gate when it's up has to be smaller than it was when it was closed and static. So that's kind of it. I don't know. Yeah, we've talked about the expressions. I won't go through this because I don't think we have time. If you want to, you can go through last year's class where we did get to this without our snafus. This is just a question asking you kind of the same thing. What force do you have to apply if you want to be able to hold this squirting monitor in place? And the same idea happens. You draw a control volume around it. It's actually on this one shown in the dashed line. This control volume here is just the dashed line that goes around it. But you have to be able to draw two things. If I zoom in on this, it's a bit too much, isn't it? Going back a ton of pages. The essence of this question is just to realize exactly what the free body diagram is. The free body diagram has a pressure applied P1, which is across here. A pressure applied, actually P2, which would be, right, if I can draw that properly. And this would be P1, and this would be P2, and it would have an area attached to it, and an area 2, and it has a velocity distribution. And the velocity distribution is a velocity V1, actually conveniently drawn on top of the velocity V1 here. So this would be V1, and this again would be A1, as this was. And I'm running out of space up here, but you get the idea that this would be a velocity V2. Hopefully it's big enough on the screen for you to see this. This would be V2, and it would have an area A2. And so this is the free body, not so different from the weir, right? So you're anchoring it, you're applying a force to anchor it, which is some magnitude Fx. And so when you resolve all these components, if I write it out in longhand, well, I guess you have to realize that P2 is atmospheric. And so you'd write out the expression. So what would it be? Sum of forces in x are equal to velocity times mass flow rate. So what would it be? It would be, forces in x would be P1 A1 plus P2 A2. This is atmospheric, so it's 0 minus Fx, acting in this direction. And this is equal to velocity 1 times velocity 1, area 1, density, plus velocity 2, velocity 2, area 2, density. And so then all you have to do is go through and figure out what your sign convention is. This is the mass flow rate, so this is coming out of 2, so this is positive. This is in the negative x direction, so this is negative. This is going into the volume, so this is negative. And this is acting in the positive direction, so this is positive. And so in this particular case, you don't know the flow rates, I think. You know the pressures, but not the flow rates. And so you have to be able to solve conservation equation, which would also be that sum of mass flow rates are equal to 0, which is rho, I'm not trying to keep you, rho V1 A1 equals rho V2 A2. And so in this expression, you have two unknowns, as it turns out, because you don't know V1 or A1, I think. You know one of them. Yeah, you don't know those. So you have to solve for those. And so you have to use conservation of mass to solve it. And you just have to be able to write this expression in terms of the right sign convention. So it's really no different from Bernoulli if you were to solve this with Bernoulli. You'd write Bernoulli equation, this is kind of the equivalent of, but it's more utilitarian because it allows you to calculate the forces that have to be applied to keep it in place. And to be able to solve this equation, you have two unknowns, and you need to resolve those unknowns by using conservation of mass. So I won't go any more than that. So it's have a look at it online. We certainly went through it last time, and it certainly exists somewhere. So I see we're 2 minutes late.